Our ancestors were cooking and smoking foods over 1 million years ago. You may think that learning to cook and to smoke food was a huge step forward, and for us it was, but for our ancestral relatives, it may have helped wipe them out. And they had crap sperm counts and they died young. The difference between them and us, the difference that matters here that allows us to eat smoked foods to this day, was just 2 carbon atoms, which is the smallest possible difference that I can think you could get between 2 genus. And if you're wondering how that's possible, I'm going to show you. Now, I'm a chef and a former scientist, and so I'm going to show you both how to get the flavor of smoke and use it in a cheap, reproducible and quick way without any fancy equipment. This is also a video on how the smallest of evolutionary steps can have the most profound difference. I'll also show you how to make some tasty and impressive mise en place with the leftovers to impress your in-laws this Thanksgiving or Christmas. If your mother-in-law is a Neanderthal, which she probably is, right? Cook this recipe instead, which is delicious buttered cabbage. So before we get to the science, we're going to cook. Now, a fantastic way to have smoke on hand whenever you want to use it is to smoke butter. So that's what we're going to do. And butter is fantastic here because its natural fattiness absorbs really well the flavors that you get from smoke, which are lipophilic and fat loving. And the second great point here is that butter is incredibly versatile. And so by smoking it this way, we get to add a potent and genuine smoky, velvety richness to anything that we want to cook with. You can use it in any way that you would a normal butter. So you can add it to soups, you can add it to purees, add it to sauces, you can bake with it in pastry and spread it on toast. Now, smoking is typically a long process, but this can be done in minutes. You just need a large pot, you want hay, you're going to need some butter and something to light the hay with. And once you've got all those things, that's all you need. Now, the things that are inward that produce this characteristic smoky flavor that we've evolved with for millions of years, that we love the smell of in the autumn air and that we love the smell of in our clothes the night after a bonfire, is because of its structural components. So we have lignin, we have cellulose and hemicellulose. And these are also present in hay. So hay is fantastic because it's got a much better surface area. It burns incredibly well, incredibly quickly, and that's why we've used it for this butter one, because we can get the smoke flavor a lot quicker, whereas wood is much more dense, it's much bigger, and without special equipment, it's tricky to use to smoke. Just a few tips. 1, make sure your butter is cold. And the reason why that's important is that the cold temperature of the butter will better condense the hot, smoky gas onto the surface and you'll get a stronger smoke flavor. The other bonus of that is that the butter isn't going to melt when you're applying smoke to it. 2, I would recommend that you burn about 1/3 of the hay each time. Get a really good burn going. And once you've got that, just put the butter on top on a plate and put down the lid. Now, you can use any fireproof vessel with a tight lid to do this, it really doesn't matter. I've used a glass lid. In general, they're going to be fine because they're tempered and the amount of heat they're going to see is actually really small, even though it's on fire. But if you're worried about that, use a metal one instead. And this is the smoked butter. Now, you're looking for a slight brown color on the surface of the butter, and that is the color of the smoke particles. Now, you might be wondering why it was that our ancestors found the flavor of smoke so delicious. Now, this was a flavor that contained molecules that ruined life expectancy of our ancestors, and yet it was delicious and irresistible. And the reason is, like other cooking processes, it produces hundreds upon hundreds of aroma molecules. And these molecules have flavors that range from fruity to spicy to woody to earthy. You name it, there's probably something in smoke that has an element of another flavor. And what this creates is perceived complexity. Now, I've spoke about this a bit on the channel previously, and perceived complexity is, I would say, a requirement for deliciousness. So how does smoking produce all this flavor? Well, there's a couple of things. First, it's incomplete combustion. Now, what that means is it doesn't go all the way to making water and carbon dioxide, which would give you sparkling water, and that isn't that nutritious. Instead, it stops before it goes all the way. And that means that you get a lot of intermediate molecules, many of which have flavor. And more than that, because it's incomplete combustion, the quality of the thing that you're using to smoke is maintained. So that's why there's a difference when you smoke with, say, oak wood, or if you smoke with pine. Now, oak is lovely and contains really subtle, gorgeous, warm aromas, whereas pine contains pinene and is really potent if you burn it. And it can be really difficult to use, and most people don't use it for this reason. Now, next up, we've got the composition of smoke itself. Now on the left-hand side of this board, we've got some broad classes of compounds that appear in smoke. And all of these combined have flavors that range from fruity to floral to woody to earthy, an absolutely delicious and irresistible mix that our great ancestors could not resist. And had this been it, had these aroma molecules all that were present in smoke, then we wouldn't have had the evolutionary pressure to need to adapt. So on the right-hand side of the board here is where things start to get a bit more deadly. We have polycyclic aromatic hydrocarbons. Now what that means in plain English, let's break that down. We've got poly, which means many, cyclic, circles, so these structures where you have the hexagons, and the aromatic refers to the fact that you have alternating single double bonds, and that is a special structural class in chemistry because it's really stable, it's completely flat, and they have interesting reactivity. And hydrocarbons means comprised of carbon and hydrogen. So interestingly, other great apes are up to 1,000 times better able to get rid of these from their system than our Homo sapiens. So if that's the case, why is it that we prospered and they died out? Well, the answer lies in a single mutation and a twist that combined may have had as much influence on the evolution of our species than any other single mutation. Here's why. Now, as is, these PAHs, like benzoapyrene, don't pose a huge amount of danger. They themselves are not as toxic. The twist comes when the body tries to get rid of them. So in all great apes, we've got what are known as cytochrome P450 enzymes, and these are enzymes that oxidize other molecules to help get them out of the system. And by oxidizing them, they become more water soluble and we piss them out. And this is what happens as normal with benzoapyrene and other PAHs. So we oxidize them with the CYP1A1 enzyme, and then this is oxidized again, and now we're in trouble. So this molecule enters the cell nucleus, reacts with DNA, and trashes the structure, and then in the cell trying to repair it, introduces a mutation potentially, which can lead to cell death or cancer. So in trying to get rid of it, this system makes a more toxic molecule, and you can see why it would be a good thing to keep the concentration of this as low as possible. And here, humans can do what no other great apes can. Now, the great apes version of this enzyme differs from our version of it by just one amino acid. Now, these enzymes are made up of hundreds upon hundreds of amino acids, and this is as small a difference as it is possible to get. So the great apes version have got alanine, which is a slightly smaller amino, or it's actually the second smallest amino acid, and the human version has got valine, so that's got a slightly bigger carbon group on it. And that has the effect of taking up a bit more space in the active site of the enzyme, which means that the benzoapyrene and other PAHs that you're trying to oxidize to get rid of can't fit in there as well, which means that it reacts slightly slower, and therefore the concentration at any given time of this oxidated product that reacts with DNA is lower in humans than it would be in great apes. Now, it's hard to see what's going on in this enzyme, but I'm going to show you how a small change in the molecule can make a huge difference into how well something can fit in there, which it needs to do to react. So this is the Neanderthal enzyme. That's the active site where a molecule needs to go into to react. And this is our molecule. So this is the benzoapyrene. Now in the Neanderthal, it fits really well, and that means it can react fantastically, there's good contact, and then it can leave once it's reacted. If you add a slightly bigger group on the inside, which is what is there in the humans, you've got a tiny little projection in this active site. And then when you try and stack the cup in, it only goes in that far compared to where it went in before with the Neanderthal version of the enzyme. And that difference is enough that you get 1,000-fold decrease in the reactivity of the human one, which means that this disappears at a much slower rate, and the cancerous molecule is produced at a much lower concentration. And so, as an analogy, it's a bit like stopping a car by crashing into a wall if you're a great ape, or it's like applying the brakes a quarter of a mile before the wall in humans. You still bring the car to a stop, you still get rid of all of the PAHs, but in doing it slower, you induce less damage. And therefore, the effects that humans suffer because of this is less than what the Neanderthals would have faced. So now you know how the flavour of smoke and our discovered love of cooking may have helped humans have an edge over other great apes when it came to the survival and thriving of our species. And if for some reason none of this has put you off eating smoked foods, then let's make some more stuff. Let's make an ash salt made from the completely charred, burned remains of the hay that we had earlier. So all we're going to do is put it into a blender, blend it, then we're going to pass it through a sieve, and now we've got this ash dust. And then we're just going to mix that through some Maldon salt or other finishing salt that you have, and you can put that on your food to season it right at the end. When you've barbecued a steak or if you've char grilled some vegetables, put a bit of this salt on, it's magic. So thanks for watching today. I hope you found it useful and that you're going to go off and make some smoked butter. I'd love to see how you're using it. I hope you found it as interesting as I have, and I'll see you in the next one.